This will be the start of a rather big section in grade 10, namely functions. Now in this lesson we're going to look at the introduction and just some basic properties. Now as an overview of this lesson, we're going to look at function input and output, then expressing relationships between variables, then domain and range, then to determine whether something is a function or not, then function notation, and then function transformation, and finally practical applications. All right, now we know actually we are acquainted with functions from primary school already. We know flow diagrams, and flow diagrams is a very simple form of a function because we have our values on the left hand side that we put into our flow diagram, and it gives us the values. It gives us the values that come out on the other side, and the values on the left hand side is known as our input values, whereas the values on the right hand side is then known as our output values. All right, so we also have this normally a box, and then you put the input value into the box, and then you just do the calculation and it gives you your output value. Now from grade 10, or when we work with functions, this unknown value, we are going to replace it with a variable. So we're going to call it x, and then we can write down this relationship between the input values and the output values into a function as follows. We can say y equals to 3x minus 4, and we are acquainted with this already from grade 9. This is then the function of a straight line. So we then call the input values our x values, and the output values we call our y values. Another name for them are the independent variables, or our x values, and then the y values become our dependent variables because it depends on what x is, what y's outcome will be. And then finally, we are going to look at this in much more detail later, is the domain and the range. All the x values that applies to your function is known as your domain, and then the y values of your function is known as your range. Okay, now expressing relationships between variables. Now here is just another practical example of another flow diagram where we have our input and output values. Now there are various ways that we can actually express these relationships with each other, and the first way is a mapping diagram, which we will just briefly look at. We won't really use that in the future. Set of ordered pairs, then table of values, then the function, and then the graph. Now first of all, a mapping diagram, what that looks like is just we have all our input values on the one side, and we have our output values on the other side that applies to our function. And what we just do is we just take our independent values and we map them to the outcome that they give. If we have our function, then this, if I put this into my function, it will map out 9, and then same 0 will go to 1, and 1 and minus 1 will go to 3. All right, and then if we look at the set of ordered pairs, this is something we're going to use a lot, where we have our coordinates. This is also known as coordinates, and the first value is always your x value, and the second one is always your y value, and we can plot these coordinates and then on a Cartesian plane, and that will then give us our graph as well. Then something we're also familiar with is table of values. We have our input values at the top, and then we just list the corresponding output values in the second row. And then the last two is particularly important. We're going to work with that quite a lot. So the function is just our function where we have y equals to 2x squared plus 1 in its algebraic form, and then we can represent that function in its graphical form as follows. Now there's a few ways we're going to graph our function, and one of the ways is where we use our set of ordered pairs, where we simply plot the points and connect the dots, but that's just one of a few ways to do it. Alright, so those are then the ways of expressing the relationships between the variables. Now let's go over and look at the domain and the range. This is also a very important section. So the definition of the domain is it's the set of all the input values of a function, whereas the range is simply the set of all the output values of a function. So if we look at some practical examples, if they say list the domain and range for this function, now this is just obviously the function in the form of its coordinate points. So what I'm going to do is I'm going to say, okay, the domain will then be my x values. What are my x values? My x values are -3, 1, 0, -1, 0, 1, and 3. So I just list my x values because that's the applicable domain. Right, and then we do the same for the range. My range is then just my y values. So what y values do we have? Now, if we look closely, we have 9, 1, 0, 1, 9. So there's 9, we can see twice, but we don't have to actually write it twice because 9 will be enough to represent all the y values that applies to our function. So we can just say 0, 1, and 9. That is actually where our function then exists in the range. Okay, now more common that we're going to get is we are normally given the graph of a function. And then we have to read off the domain and range from our graph. Now, here we have 3 points. As we saw with the previous example, we had our set of ordered pairs. Now, normally we're not going to work with just points. We are going to work with our common functions. This will just illustrate the point basically. So when we look at this point, we can read off the graph that we have x values of 1, 3, and 5. So that will then form our domain. But for myself, what I do is I just imagine that a light is being shined from the top. So if we shine a light from the top, what happens is the shadow will then fall wherever the graph exists. So here we can clearly see that 1, 3, and 5 then forms our domain, and we can do the same also for the range, where if we shine a light from the right hand side, we can see that our range that applies is 2, 3, and 4. Okay, but like I said previously, we aren't really going to work with just points. We are more interested in functions, like for example a straight line function. Now the straight line functions we are accustomed to in grade 10 are not restricted. They go from negative infinity to positive infinity. So this is an example of a function that's restricted from a certain value to another value. So if I shine the light from the top, I can see that the shadow will fall from 1 to 5. So that means the domain of this one will be simply from 1 to 5. And then another thing that can happen is but we'll look at some practical examples later. I think for now we can just assume that this point 1 is included and this point 5 is also included. But there are cases where the points are not. But for them both being included, if I write my domain, then my domain will simply be from 1 being less than or equal to x being less than or equal to 5. And we can write it like this, and notice that we say less than or equal to. That just applies to because both of these points are included. Or we can say for the domain in the interval notation, this was the set builder notation, or if we want to represent it with the interval notation, we say x is an element of, then a square bracket for it being included. Remember, if a value is not included, it's a round bracket. So square bracket from 1 up until 5, again included. Okay, so let's have a look at the range. If we look at shining a light from the right hand side, now be careful because we all tend to think about like the way we read from top to bottom. But remember, this graph is numbered from bottom to top. So when you're going to actually state what the range is, always remember to read it from the bottom upwards. So it's not going to be from 4 to 2, it's going to actually be from 2 to 4. So if I should write out the range, let's start with our set builder notation. It's going from 2, assuming that 2 is also included. It goes from 2 less than or equal to y, because we're now working with the y-axis or the range, less than or equal to 4. And our interval notation will say y is an element of, including 2 up until 4. Right, so that's basically how we represent that algebraically. Alright, so the next section we're going to look at whether something is a function or not. And not all the relationships between the input values and output values actually define a function. And the question we want to answer is, what relationship between input and output values does not define a function? And how we're going to answer that question is we're going to look at the following: that for any function, every input value has only one output value. And then also, different input values may have the same output value. So this is quite a mouthful, and it's hard to actually see this when you just read it. So the best way to describe this, firstly, is if we look at a table of values, we can see we have our input values, -2, -1, 0, 1, and 2. Now, each one of them, they only have one output value. So -2 only has one value, namely 9. -1 only has one value, namely 3, and so on. But the second statement says that different input values may have the same output value. So if I look at -2 and 2, they can have the same output value. So they have both 9 and 9. And also -1 and 1 also has 3 and 3, same. So different input values may have the same output value. So this can still be a bit rough around the edges to understand. And once we look at the graphs, it becomes actually very clear how it works. If I look at these two examples, we have this one where if we look at -1, 2, 3, -4 over here, we can see that there are a lot of values that lies on -4, and the same for 3. There's a lot of values, output values that -3 gives. So if a function can't have more than one output value for a specific input value, so meaning this guy is not a function. But if we look at this one, we can see that each and every input value can only give us one specific output value. So in this case, we do have a function. So this is a function. Now, one way of looking at it or to test it is the vertical line test. And what that basically means is you take your ruler and you go over your function vertically with your ruler. So I can draw a line there, or well, you won't actually draw it, you just drag your ruler over your function. And if your ruler cuts the function more than once at any point, like here we cut it infinitely amount of times, so here we have 1, 1, 1, and then here again infinitely amount of times, then it's not a function. But like let's take our ruler over this function, then we can see only cuts it once, wherever we go. It will always just cut the function once. Therefore, this is a function. Second example, we can look at the semicircle. Now, if I drag my ruler over here, we can see there's two values for 1 or 2. There's actually two values everywhere. So meaning this is not a function, whereas this one, for each and every input value, we only have one output value. So this one is a function. Right, now function notation. Okay, so this is quite an important section. From grade 9 we know y equals to 5x plus 3, and that's basically how we define a function. But from grade 10 and onwards, we always work with the new notation, and we're going to, instead of writing y, we write it as fx. It just helps us to write it as, and this f is not particularly, it doesn't really say function of x. F is just a name of the function, although I think they always use f because it just looks like function of x. But this can also be g or h. It's just a specific name, and what this helps us with is now we can have multiple functions where we can identify between the two. So we're not just going to say y equals to this. We can now say f of x is equal to this, g of x is equal to this, and we'll have different functions with different names which we can identify them by. So here is what it will look like then. F of x is equal to 5x plus 3. Right, now what is also handy about this notation is when you have a specific value for x, we can say, let's say x is equal to 1, then we can substitute it in as follows. We can say, what is the value of f of 1 then? So this will then give you your y value. So I just then substitute in x, my x value into my function, and it gives me 8. So the way we actually say this is for x equal to 1, the corresponding element of the range is 8. Or we can just say that f at 1 is 8, or we can just say that the function value of f at 1 is equal to 8. Right, so let's look at these examples, just basically basic substitution. So for a, if I have to find f of -2, I substitute it in. I have 3 times by, in place of x now, we have -2 squared plus 2. And here we can work that out. You can type it in your calculator, but this is quite basic. -2 squared, remember the square makes this a positive. So 3 times 4 is 12 plus 2 is 14. Okay, and then to find f of 3, where x is equal to 3, we simply substitute it in again. And we get 9 times 3 is 27 plus 2 is 29. Okay, so that's simple basically. So here we can say that f at -2 is equal to 14, f at 3 is equal to 29. Okay, same story here. Now we just have a straight line. So and notice here we have gx, so that's just another function. So g of 3 is then -4 times 3 plus 2. So the value there, -12 plus 2 gives me -10. And then for b, g of -3, substitute in -3 plus 2, and that gives me 14. And then finally for c, g of a third is equal to -4, substitute in a third, plus 2. Right, and this one we can actually put on the calculator. Here we have -4 1/3 plus 2. Okay, so that's 2/3. Right, so that's basic. Okay, so next up, we're going to look at function transformation, although we aren't going to really go into much detail of transforming the functions yet. We're basically just going to look at what happens with the notation. You actually you don't really need to even know that this is transformation. You can just, if they say 3 times hx, what is the new function? If I say take my hx. Now, hx represents the whole function, all right? So hx represents this entire part. So if I say 3 times hx, that means I multiply 3 with my entire function, which then means I get 3 times by -5x minus 4. I multiply them out, so we have -15x minus 12. Yeah, and that's basically then my new function known as 3 times by hx. Next up we have h and then 3x, so we have the 3 multiplied only with the x inside the bracket. So what this means is if I multiply 3 only with x, it means wherever I see x, I'm going to replace it with 3x. So negative 5, and then in place of x, I'm going to put 3x minus 4. Yeah, so that then becomes negative 15x minus 4. And then finally, we have hx plus 3. So here again, we have our entire function and add 3 to our entire function. So you take your entire function, negative 5x minus 4, and you add 3 to it. So then we get negative 5x minus 1. So this is then our new function. And for the last example, here we see that the 3 is only added to the x, which means then wherever x is, we just add 3 to it. So negative 5, and then x plus 3 in place of x, minus 4, and simplify. So multiply out your brackets and then add like terms. So this goes to both terms inside the brackets, minus 5x minus 15 minus 4. And then we have minus 5x minus 19. Alright, we are on the last section, and this is basically on practical application. Now, functions are being used a lot in real life, and one simple example of that is if I have this formula, f is equal to 9 over 5 c plus the 32. Now this formula is actually used worldwide, and what it is it goes from it translates from your degree Celsius to degree Fahrenheit and vice versa. So what we do is, if we are here in South Africa and we use degree Celsius, so if you have a friend overseas and you need to or want to basically let them know how cold we are today, you can basically just lost the word, convert, that's it. Convert the degrees to Fahrenheit, or they can convert Fahrenheit to degrees. Another place where this is used a lot is obviously in science, for the standard unit of measures. Alright, so let's just look at the example. If we say convert 15 degrees Celsius to degree Fahrenheit, what I'm going to do is I'm going to, now to go from Celsius to Fahrenheit is quite easy, because the function is already in terms of Fahrenheit, is already in terms of degree Celsius. So we're going to say Fahrenheit, or the f, is equal to 9 over 5, and then multiplied by 15, or just substitute in 15 for degrees Celsius plus 32, and then work it out. Okay, so that gives me 59. And remember your units, it's in degree Fahrenheit. Now for the second question, we see that convert negative 25 degree Fahrenheit to degree Celsius. So now when we substitute, remember to substitute into the f for Fahrenheit. So we have minus 25 is equal to 9 over 5 c plus 32. And this one is just one step harder, because now we have to just solve for c. And this is just a linear equation in which we take all the constants to one side and our variable on the one side, and then just get rid of the coefficient. So let's take the 32 over to that side. Negative 25 negative 32 is equal to 9 over 5 times by c. So simplifying that, this gives me negative 57 is equal to 9 over 5 c. Alright, now a fast way of getting rid of this fraction is just to multiply it with its inverse. So just multiply it by 5 over 9. You could do it in two steps by first multiplying both sides by 5, then dividing by 9, although this is just faster So what we do on the one side, we have to do on the other side, and we multiply it with its inverse because now this and this will cancel. So here our answer now, C, is equal to negative 57 times by 5/9. Okay, and that gives me, let's rather put it in decimal places, negative 31,67. And we are in degree Celsius. Okay, we are finally done.